is first, anytime you have electricity, you can induce magnetism. Anytime you have a magnetic field, you can induce electrical flow. That's why they call it electromagnetism. Okay? They go together. All right. So when we, by the way, was that a pretty good video? Yeah, I thought it was really good when I saw that. I'm like, gosh, that really worked pretty well. And that gives a good overview of some of the things we're going to cover today. All right, so your sources of electrical energy in an airplane, or in any system, if you will. Magnetism, of course, you saw that as a source, right? Chemical, there's your battery. Heat, it's really hard to stick something into a piece of metal into, say, a cylinder, okay, or on the cylinder head, if you will, because it's so hot sometimes the metal will melt, okay, or you can't stick a thermometer in there because you blow the mercury right out the top, right? So what they'll do is they'll just take a wire and put it in there, and that change in heat, okay, from one place to another will actually induce electron flow. Okay, so there's where your thermistors come in, therm, heat, okay? And so heat will actually generate electrical flow. Pressure will, okay? Everybody's got a microphone in your computer and all, and I'm talking on a microphone on my phone there, this video in this thing. That has what's called a piezoelectric crystal in it, okay? And when the crystal gets hit by my sound waves that I'm talking, okay, it's a vibration, right? So what's the crystal do? In response to the sound vibrations, it vibrates, okay? And that vibration will actually induce a electrical flow from the crystal, okay? And then, of course, you put that into an amplifier and then put it into a speaker, and sure enough, you have taken sound waves and converted it through electricity back to louder sound waves through the speaker. Oh, by the way, how's the speaker work? Magnets that vibrate. Okay, actually vibrates the speaker. So, pressure will, in fact, if you've got the right piezoelectric transmitter, okay, or it's actually a quartz crystal, it will, in fact, induce electrical flow. And the last one is light. Y'all are seeing the solar farms that are popping up all over the place. Big one out in Jackson Springs, big one up in Carthage, big one right by my house down Airport Road, or Camp Easter Road, down between Lakeview and the school, new school. They got huge, and there's one out in Niagara Carthage Road too. So I mean, they're popping up all over the place. So the photocells themselves, through a chemical reaction, okay, will induce, from the light, will convert to electricity, okay? And so all of those can be sources. Now the ones we're going to work with mostly, batteries, okay, and generators. Okay, so electricity and magnetism in aircraft. Make sense? Those are the two that we're going to normally work with. Okay. So where did we pick up the other day? We picked up right here. I believe slide 17 is where we'll go to. Let's see. Yeah, there's our sources. I do believe, let's see, from current slide, there we go. Maybe, there. This is where I think we left off in our last Thursday session, at least I think we did. And I just went over this, chemical energy, heat, pressure, light, we got that. Now we have to define a circuit, all right? There's really only three things that you need in a circuit, all right? You need a source, something to push the electrons. You need a closed circuit, which is your line here. And you need a load or resistance. All right, those are really the only three things. Depends on what you want to do with the electricity. Okay? Now the wire will give you natural resistance. All right? And then of course, when you have the source and you have a path for the voltage or energy to flow, you will create a current. So you notice there's three things there. There is voltage, and you'll see it as E, or electromotive force. You'll see it as current, that's the actual electron flow. All right?
Which is measured in amps, right?
And it's measured in amps, that's correct. And then the resistance, which is measured in ohms, okay? And the resistance is just something to slow down, if you will, the electron flow. And they use resistors like this to control how much amperage you have going through, or how much electron flow you have going through the circuit. All right? You know, if you've got a 30 amp circuit, you know, you don't want to overload it. All right? Or if you have a 30 amp, or an 18 amp air conditioner, you don't want to run 30 amps running through it. Okay? Because you will do what that thing did to that wire that kind of blew itself up. Okay? All right, in video. All right, so the parts of a circuit you need to understand. 1, 2, 3, 4, 5 parts, okay? And you need to know what each one does. Your source, whether it be a battery or a generator, is what creates your voltage, okay? Or it could be a photocell. Who's got a calculator that's got the little light cells on it? I do, okay? Yeah. So that is your source. Your load is any device that converts the electrical energy to a different form of energy, such as a motor, right?
So that's what
converted to mechanical energy.
Is that what the circuit would be connected to?
Mm-hmm. Yeah, you would have your lead here that would go to whatever your load would be. In this case, okay, and I'll talk about this later, when I flip this light on, I just activated and closed the circuit, didn't I? Okay? Now I'm going to turn it back off. I just opened the circuit. Why? Because you have to have a closed loop for the electrons to flow. Okay? You have to have a place for it to go. If that circuit is open, obviously, right now this circuit's open because of the switch, then the electrons will not flow. It's got to have a closed path. That's a big deal. All right, so, you know, a fan. You know, what do you have in an aircraft? Fan motor, pumps, hydraulic pumps, your gear, if you've got a complex, you know, your gear motors, your flat motors, all of those, in fact, are loads. Conductors, again, is your wiring, okay, and we'll talk about the types of wiring in an aircraft in a little bit. That's your path, okay? And of course, around the conductors, you're going to want to have insulators. Okay, so you don't short the path. Right? So you want to determine what the path is. A switch is any device that opens or closes that circuit. And over here, where we talked about a solenoid, that can be a switch. Right? You can have a switch here. Right? These light switches, that's what they're called, right? Switch on, switch off. Those are, in fact, switches. And they are just, it's something on the circuit that can open and close the path. Then protection, again, it can be a circuit breaker, it can be thermal, it can be fuses, it can be resettable or not resettable. Most of the ones in the aircraft are, in fact, resettable. Okay? In your house, you've got the circuit breakers that pop and you reset them, right? Some older houses have the round fuses that, you know, once those things burn out, they're basically thermal fuses. You know, you got to screw it back in. In your car, lots of thermal fuses, little 15 and 5, 15, 20, and 30 amp thermal fuses.
I had to replace one once because my brother blew out the car charger fuse because he short circuited. He literally took the charger cord and plugged it back into like the charger itself for no reason, and all of a sudden there was a spark and
He shorted it
He
around.
shorted the fuse, and I went and replaced it, and I could see where it was broken
Yeah.
inside, so
And
that was pretty cool.
so when it breaks, what's it do? It opens path. Okay, and that's what the protection's all about. All right, and then, of course, in an airplane, normally, in a 172, you've got a whole panel of circuit breakers up here on the board, okay, up on the dash. In more complex aircraft, like King Air, they're all up here on the overhead. A whole bank of circuit breakers. And it's nice to know when one pops what it's connected to. Don't you think? This is why you study an aircraft electrical system. What's wrong with that thing? I don't know. Put it back in and hold it back in. And watch it smoke. Okay? I've had a couple of young pilots in the Huey smoke up a Huey like that. All right. So conductors, again, provide for your electron flow. And in an aircraft, how are we going to select our conductors? I mean, you got wires all over that airplane. Look at that wing. Okay? Again, you got wires. If you got a complex aircraft like this, that looks like an airline wing, you've got slats, you've got ailerons, you've got your hydraulics, you've got flaps, you've got, all kinds of different motors that are going to run in here. Well, you got to get wires to them. What's the main concern for designing aircraft? Any aircraft? Weight. Okay? Always weight. Okay? So you also want to have minimum resistance so you can have it light and you can minimize how much source voltage that you have to put into the system. It has to flow through the load to produce your work or power. Has to be a closed loop, we've already said that. Aircraft must be designed with a single, or can be designed with a single wire system. That means the wire goes out, goes to your load, goes all the way back to your source, be it a battery or generator. Now, some aircraft have what's called a single wire system. Since they're made of metal, okay, a lot of times they'll have the wire go out to your source.
And it doesn't come back?
It'll come back by the fuselage, okay? If the fuselage is made where it is metal and conduct electricity, that's called a single wire system. You save half your wiring, don't you? Wait. So they will actually use it and hook it up. That's generally true from smaller general aviation aircraft. I don't think you'll see that in big, complex aircraft. And of course, in composite aircraft that's made of fiberglass or composite resins, it's not going to conduct anyway. So you've got to actually create a bonding strip, metal, which can act as your conductor to go back to your load, or source, excuse me. Source, load, and remember you have to have a closed loop. So you have to have something that goes back to your source so the electrons will flow. Okay, does that make sense? So you got to have a closed loop when you build that thing. All right? So the circuit elements, okay, the design must consider resistance in a conductor. Okay, so your first was a source, next is your resistors. Okay, and you need to understand what affects resistivity. Ooh, man, look at that science thing. Got a little Greek P right there. It's not pi, but it's rho. And so the things that that you're looking at with your design is how long is the wire. Okay, the longer it is, the more resistance, right? Okay, the more electrons it has to go through. In fact, right there, length over cross-sectional area. Oh, look at that. Cross-sectional area is on the bottom. So that means the bigger the gauge wire, the lower the resistance. Okay? But what are you trading off with that using a bigger gauge wire?
More weight.
Weight. Okay, yeah. All right, so rho is the resistivity itself, okay? And that's based on what kind of metal it is. If it's copper, it has a lower resistivity than aluminum, better conductivity, right? Which is different than steel. All right? And so the three main metals you're gonna see in an airplane anyway are aluminum, steel, and copper. Those are generally what this is gonna be. You may see some magnesium. Magnesium burns, that's a problem, okay? But normally what you're gonna see in the airframe is steel, aluminum mainly, and copper for the wiring. Does that make sense? Okay? And again, and resistivity is basically what the metal is, how long the wire is, and then how wide or thick the wire is. And that's going to determine your resistance. Okay? So 0 gauge is the largest and 40 gauge is the thinnest. Okay? Remember, he said in the video, the larger the number, the thinner the gauge, or the thinner the wire. Okay? Of course, the cross-sectional area is twice the diameter, right? All right. And then, or is it 2 pi r or something like that, right? Anyway, so the resistance is KL over S, and that's basically this thing right here. All right. Resistance in ohms, K is rho is the resistivity of the chosen metal, L is the length of the wire, and S or A is the cross-sectional area, and that's how you figure out the resistivity, okay? Now, what do I want you to know on this one? I want you to know what affects resistance in a wire. Am I going to make you do problems on this one? No. But if you tell me, hey, what the metal is made of, how long it is, and the cross-sectional area determines the resistance in a wire. If you know that, you're good. Okay? I might ask you, hey, if I increase the area, okay, what's that going to do to the resistance? What is it going to do? It's on the bottom, so that number's going to get smaller. Okay, so by increasing the area, the resistance goes down. By increasing the length, the resistance goes up. That I do want you to know. Okay? Y'all go with that? So you know what I want you to know, right? When we talk about resistivity or resistance. Okay, next. Circuit elements. Again, these are switches, okay? And there's your switches there. A couple switches there. There's your rocker switches there. There's your pole switches there. And so switches, there are many types of switches used in an aircraft to control the circuits, to open and close the circuits. Depends on the type of the function. Like in a Huey or most in the King Air was the same thing. To start the engine, you would take the starter and push it over. It was spring loaded, and the starter would start running the engine. As soon as you let it go, it was spring loaded to come back off. Okay, so that close is a switch, but it's a normally open switch. We'll talk about that in a minute. That's spring loaded that you have to hold it down to close the circuit. Okay, so what you do, you hit the starter, let the engine run a little bit, it's a gas turbine, and then you introduce the fuel. Okay, the igniters are popping, boom, 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 boom. Okay, and then lights the fuel, let it off, the igniters go off, and it's self-sustaining. Yeah.
Would the master switch be an example of double pole, single throw?
Depends on how many buses it's running.
Okay, because if it takes both of them to turn it on.
Yeah.
Gotcha.
It would probably be double throw if you've had 2 buses in a smaller aircraft like that. It could be even more, okay? When you talk about a double throw, well, single throw, here's a single throw. Okay, make sense? There it is. You'd open and close the circuit. That's a single throw switch. If I hook these two together, guess what? If I put a little bar on across there and switched them both, now my finger's the bar. Double throw. That's 2 singles that are hooked together. It is that easy. Okay? So, we'll talk about that in a second. All right, so the switches can be simply on and off switches. They can be rotating switches, right? They can be variable resistance, which would be like a rheostat he showed you in the video. So they can also be change direction of your current. Like this one right here, actually up does one thing, it's in a neutral position, and down does another thing, okay? So depending on what it's hooked to, it can actually reverse the polarity or the direction of the flow of the electrons. Okay? There you go, there we're talking about. Single pole is a light switch. Am I gonna ask you a whole bunch about this? No. What I want you to know about that is that you can control one circuit with a switch, or you can control multiple circuits with a switch. Okay?
Or the other way around, right? Like you can make it where it needs two switches to open one circuit?
Yep. Mm-hmm. Yep. Okay, it depends on where you put them in the circuit. Okay? And we'll do a whole lot more with that. Okay? Switches, again, different types. I do want you to know the different types of switches. Rotary switches, normally closed or normally open switches. That's when the switch is not activated, the circuit is open. That means you don't have any flow. It's like the starter. Probably the starter circuit's a good example of a normally open switch. Okay?
So,
If you have a, go ahead.
so when we have to put, some of the systems I work on at work, we have to put normally closed, normally open for freeze protection.
Right.
In other words, if the unit freezes, you've got a normally open solenoid, but once it freezes, it shuts down the system.
That would be normally closed.
Normally closed, right?
Yeah, that would be normally closed. Exactly. Okay, and maybe you have a protection, something like that, that if you have a fault, it activates the solenoid and it
Shuts the
opens up.
water down to the system, so it
Exactly.
doesn't
Mhm.
flood.
Perfect. Works the same way. A normally closed system would be a full circuit unless you want to turn it off. And then you throw the switch to turn it off. Okay? But in a normal, everyday usage, that light or whatever you're using is on. Okay, that's a normally closed system. Push button switch, again, stationary, there's different kinds. You can push it down, it stays down. You can click it, and it comes off. So different types of push button switches. Relays and solenoids, again, I've talked about those a bunch, are basically electromagnets with a spring. Okay, and it uses the magnetism to activate the solenoid. There's a good picture of the solenoid right there. Okay, and these can be normally open or normally closed. Okay, depending on what you're doing with the circuit. All right, next. Here's your protecting devices. There's your thermal fuse that we talked about. You can have a fuse that just opens a circuit in different ways. Glass tubes, there's your fuses. You can have slow blow fuses, which are basically spring loaded, and then you can automatically reset. There's on the panel there. Okay. And then you can also have circuit breakers, which are generally resettable. Okay. And each circuit breaker will be rated for a certain amperage. So if you get a greater amount of flow through the circuit than what it's designed for, to protect your load, it's going to blow the circuit breaker, or it's going to pop the circuit breaker, or blow the fuse. That's probably better. Blow the fuse or pop the circuit breaker. If the fault still exists, a good rule of thumb in an aircraft: reset the circuit breaker once. If it stays in, you're good, right? If it pops again, leave it alone. And never, ever, ever, ever hold a circuit breaker in, because obviously there's a fault, right? Okay? You will fill that cockpit with smoke right now, all right? And burn the thing up. All right, variable resistor is like a rheostat. All it does, it's kind of cool. It changes the length of the resistor, which increases or decreases the resistance in the circuit, which allows a higher or lower amperage or current which basically the light goes bright, the light goes low. It's like if you got in your dining room a dimmer, that's the same thing. And they've got them in the airplane as well.
And windshield wipers, right? Like with the different speeds?
Yep. Mm-hmm. It's a variable resistor. Okay? So that's your rheostat. Potentiometer a rheostat actually adjusts the current by changing the resistance. A potentiometer adjusts the actual voltage, okay, in a given circuit. Okay? A radio volume control is a potentiometer. Okay, because it actually, like if you got, say you got a portable radio with 12 volt battery, right? You want to turn it up, crank up to 12 volts. That gets you hold your volume. You want to turn it down, right? Then it actually changes the voltage, and then the strength of the current is changed by varying the voltage. That's your potentiometer. Make sense? Okay. All right, we'll stop right there, and if you don't mind, yeah,